Hi folks, here's our first YouTube live review for Calc 1. So there's a chat box over on the right hand side. If you have any questions along the way, please go ahead and ask them. This was updated in terms of questions that I saw up into an hour ago. So if you have any questions, kind of toss them in there, and there's some coming up on all sorts of different topics. So without further ado, let's get started. So we have the greatest integer function graphed here, and we want to evaluate the following limits. And so, oops, let me bring that up. Okay. So we have the limit as x approaches 3 from the left, and then limit as x approaches 3 from the right of this greatest integer function, the limit as x approaches 3 of this greatest integer function. So let's start with the limit as x approaches 3 from the left. So notice each of these has some form of a hash mark right there. So this is 3 sitting right here. And if we're to approach it from the left, let's see if I can maybe bring in another color. Okay. So if we're approaching it from the left-hand side, we're getting closer and closer to some y value right here. So what is that y value? Well, if you notice, this is 1. And so that y value is 2. So the limit as x approaches 3 from the left-hand side actually equals 2. In a similar manner, we can do the limit as x approaches 3 from the right-hand side. So here's 3. We want to go to the graph and we want to approach it from the right-hand side this time. And as we go from the right-hand side, notice we're getting closer and closer to a y value that corresponds to right here, which is 3. So the limit as x approaches 3 from the right-hand side happens to be 3. Okay, so now what's the limit as x approaches 3? So the real question becomes, with this left and right-hand limit, are these the same? And if they are, that's going to be your limit as x approaches 3, because this is including both the left and the right hand side. But since they aren't in this case, this is a does not exist scenario. And so what we try and do in mathematics oftentimes is generalize this idea. Now, one example does not constitute a solution for all. So what we try and do is we can look at all sorts of different examples. Let's look at negative 3. For example. So what's the limit as x approaches negative 3 from the left-hand side of f of x? And what's the limit as x approaches negative 3 from the right-hand side of f of x? Well, from the left-hand side, notice this is negative 3 right here. So when we draw this dotted line on down, from the left-hand side, we're going to start to approach from this side. Now notice that's negative. There's negative 1, there's negative 2, there's negative 3, and there's negative 4. So from the left-hand side, this is going to be negative 4. And then from the right-hand side of that line, notice we're on the graph, and then we're approaching what y value are we approaching? Well, it's negative 3 in that case. Okay, so notice the limit as x approaches negative 3 doesn't exist as well. But what's happening in general? Well, the easier part should be when we approach from the right-hand side. So if a is an integer, evaluate the following. So we have a being some integer. From the right-hand side, notice we had 3 from the right and our answer was 3. We had negative 3 from the right and our answer was negative 3. So if we have a from the right, we're going to just have a being our answer in general. And then from the left-hand side, we got to figure out a formula. How do we go from negative 3 to negative 4? And how do we go from 3 to 2? What's happening here? Well, in order to go from negative 3 to negative 4 and from 3 to 2, notice 2 just is 3 minus 1 and negative 4 is just negative 3 minus 1. So in general, a from the left-hand side, if it's an integer, will be just a minus 1. Notice these two values are not the same, so the limit as x approaches a of f of x will not exist for any integer. And that's how we go about solving these problems. We try and take some ideas, work a couple examples, and then generalize, and so on and so forth. Okay. So now you might start to see some changes from what you're seeing in your own homeworks. I try and make a few changes here and there. So if this doesn't look identical to what you're seeing, I'm just making some slight changes, but the same type of problems. So now let's talk about one-sided limits. Evaluate the limits of f of x equal to this piecewise function, a times the quantity x minus b raised to the fourth power plus some c if x is less than b, and a times the quantity x minus b plus c if x is greater than b. So notice, when we approach b from the left, this means that x is less than a b, and that's where we're approaching, versus b from the right means we're starting with x greater than b and approaching from that side. So if x is less than b, what this becomes is the limit as x approaches b from the left of, well, if we're talking less than b, that's this scenario, so that would be a times x minus b to the fourth plus c. Right? Notice we aren't using another one because we're talking less than b and not greater. So at the end of the day, what happens here? Well, you can just plug in b and see what happens. So this should equal a times the quantity b minus b to the fourth power plus some constant c. Notice b minus b is 0, so a times 0 is just 0. So this just equals c. In a similar manner, what's happened is you have the limit as x approaches b from the right-hand side. Well, we're talking x greater than b, and so that's the second scenario. And so the function we're going to use is that second function. So no longer having the fourth power in there. So this is just a times the quantity x minus b plus c. And so that would equal a times b minus b plus c. And so that equals c as well. So notice we always check to see if the left and the right hand limits are the same. They are in this case. So that means the limit as x approaches b is actually equal to, limit as x approaches b of f of x, I should say, actually equals c in this case. And what happens, now there's different scenarios depending upon the values of a, b, and c, right? But so to give you a general idea, here's what's going on. For x less than b, so what that's done, that x minus b business, we've shifted some units b to the right, and then we've shifted up so many units c. And we have this little hole sitting right here, and then our graph, a x minus b to the fourth, so I'm assuming that b is positive and both c is positive, and a is positive, I'll do here. You get something like this, and then from there on out you get something with slope a, so I'll just say it's something like this. Now granted, it won't look like this necessarily in general. It's all dependent upon the scalars that you're using. It could be thinner, it could be rising even faster on that linear equation, but that's in general what this thing looks like. And so if you notice, we approach it from the left, we get c as our y value. If we approach b from the right, we get c as our y value. That's essentially what's happening there. So don't see any questions, so I'll keep on moving, but once again, if you do have anything pop up, just put it up in that chat box. I'm happy to help. Okay, so now we'll get into this velocity idea, in particular average velocity. So you have this ball thrown into the air with a velocity of 40 feet per second. Its height is given by y equals 40t minus 16t squared. And so we're talking acceleration due to gravity and things like that we have to get involved to create that equation. We're going to learn how to do that a little bit later. But for here, we want to find the average velocity. So for the time period beginning with t equals 2 and lasting 0.5 seconds. So that first one, notice what we're doing. We're going from 2, and if we last 0.5 seconds, that means we go to 2.5. And how do we find this average velocity? Well, when you think about it, we go this f of b minus f of a all over b minus a equation. That's the average rate of change. So essentially, all we need to do is plug in 2.5. So f of 2.5 minus f of 2 all over 2.5 minus 2. And so you just plug it in, and so you get 40 times 2.5 minus 16 times 2.5, the quantity squared. So that's all f of 2.5 minus, so now we go 40 times 2 minus 16 times 2 squared all over 2.5 minus 2. And so this average rate, or average velocity, I won't shorthand it here. What is that going to equal? Well, you can plug that in a calculator or whatever you might need be. So 40 times 2.5, I believe that's 100 minus, so 2.5 is 5 halves. 5 halves squared is 25 over 4, so 25 over 4, so that should be 100, I believe, as well. Minus, so this will be 80 minus 64 all over 0.5. Okay. And so what happens here? So we have 80 minus 64, the 100 minus 100 cancels out, so we have negative 16, or negative, yeah, 16 divided by 0.5, so that becomes negative 32, and this should be in feet per second. Okay? Now for our next one, let's take a look here. So for, in this case, where's our interval? We're going from 2 to 2.01. Okay? So in this case, all we need to do is go f of 2.01 minus f of 2, which we already know what that's going to be. That's going to be 16. And then you have 2.01 minus 2. So in that case, f of 2.01 we will have to plug in again. So we have, what is that, 40 times 2.01 minus 16 times 2.01 squared. Yeah, and so I just saw a thing that says, hey, can I go back to the previous problem when I finish this and explain again? So b equals 0. Yeah, I'll try and touch on that in just a second. Oh, my mic's humming badly. I'm sorry. I really don't have much control on that. Let's see. I'll try and test that. Is that any better? Yeah, my apologies if my mic is humming there a little bit. Not my intention. Hopefully that'll fix it. So on the next part, minus the f of 2. So let's see here what we got. F of 2 was 16. Okay, and then you have 0.01 going on, is what you're dividing by. So now it's just kind of a plug and chug thing. So 40 times 2.01 minus 16 times our 2.01 quantity squared. So that should equal 15.7584. And then we want to subtract off 16 and divide by 0.01. So minus 16 and divided by 0.01. And so notice this will be equal to negative 24.16 feet per second. And what can happen is we can take smaller and smaller intervals. So instead of 2 to 2.01, and then you could do 2 to 2.0001, right, and keep on going on down the line. What happens is we're getting closer and closer to this idea of instantaneous velocity. And so what we really want to do is, instead of taking this in general, we want to take the limit as b approaches 2. And what that means is we'll have this f of b minus f of 2 all over b minus 2. And if we're getting closer and closer with those intervals to 2, all of a sudden we have an instantaneous rate of change, or an instantaneous velocity. And this is something you're going to be building to a little bit later down the road. You don't have to do this. You could keep on doing average rates of change and kind of see where the trend is. You start at negative 32, you get negative 24.16. You'll get smaller and smaller intervals will be like negative 24.008. You'll get sooner or later, and you'll see where this is heading. But just to kind of show you what's going to happen down the road, so we take limit as b approaches 2 of f of b. Well, what is that? Well, I wrote f of b. What I could have done, my apologies, this y is the same thing as f of t. So we could have 40b minus 16b squared all over, or all minus, I should say, f of 2 we found was 16. And all of that would be over, b minus 2. Okay? And what we'll learn on down the line is there's some nice little tricks. And if you plug in b equals 2 into this, you get 40 times 2 is 80, minus 16 times 4 is going to be 64, so 16 minus 16, so that's 0, so that means a factor of b minus 2 must be sitting up top. And what might help is if we wrote this top like negative 16b squared plus 40b and then minus 16. So, and this will kind of lead into the next scenario that we're going to get into. So what we have happen here is we know, since we plugged in 2 and it goes to 0, that means we have a factor of b minus 2 when these are polynomials. Okay, so you have b minus 2 sitting there, so what's the rest? Well, you know that it has to multiply to negative 16b, so you get negative 16b squared, so you need a negative 16b sitting right there. And then what's our extra term? Well, notice we needed to multiply to negative 16. So negative 2 times what will give us that? And notice, oops, yeah, negative 2 plus 8 will actually do the trick there. Okay, and I went a little bit too long on that part. So now the b minus 2 factors cancel, and what we're left with is the limit as b approaches 2 of negative 16b plus 8. So that's negative 32 plus 8. So notice that thing equals negative 24 feet per second. Okay. So there was a request to go back to the previous problem, and I believe, let me kind of check this out real quick. Kind of go back and explain again. So b equals 0. So if b equals 0, it's actually quite simple. Then you have this whole thing changes in the case that b equals 0. You get a, and then b is 0, so this is ax to the 4th plus c if x is less than 0. And then it goes ax plus c if x is greater than 0. Right? So what happens now? Well, it's the same song and dance, right? You actually already have the answer, as a matter of fact. Notice we can replace the b with 0 of f of x. So our new equation looks different, but it's still going to be c. And that's the beauty of having some general result. All I'm using is that previous term. If you want to plug in a different c, that's fine, right? So if I wanted to do, say, f of x equals, pick your favorite a value, right? So let's say 5, and so I'll put a 5 down here. And then I could do x minus 7 to the 4th, and I'll do an x minus 7 here, and then plus, pick your favorite c value. So let's say 792. And here's another plus 792. And I have, in this one, if x is less than 7, and this one's if x is greater than 7. Here's all that happens. We just take the limit as x approaches, remember, it's supposed to be b, because you see it right there. So x approaches 7 of f of x in this case. Well, notice that's the same equation that we just had. The only difference is we have 5 in for a, the b is 7, which that's taken care of. And look at our final answer should finish with c. Our c is equal to 792, so there's our answer in that case. And that's the ideas that we want to try and pull. We want to try and pull more and more general results so we can apply them to all these specific examples. So hopefully, if that doesn't answer your question, just let me know there, Chase. All right, so if I don't see any more questions, I'm going to move on forward. So here we go. We got this one done. And now we're heading to limits by factoring. So we kind of touched on that at the end of the previous problem, the problem from the previous page. Evaluate the following limits. Limit as t approaches -4 of t squared minus 16 all over -2t squared minus 13t minus 20. First thing to do, always plug in, just make sure. Notice when we plug in, we get 0 on the top. When you plug it in on the bottom, what do you get? Well, notice you have a, when you plug in that -4 for this t, that'll make it 16, so -2 times 16 is -32. -13 times -4 makes positive 52, and then a -20, so that'll become 0 in the denominator. So we were just plugging into those two t values. Since we get 0 in the denominator, that actually tells us some information in both parts. Okay, since you have t approaching -4, right, and both of those are 0, that tells us what a factor is, a certain factor in particular. So limit as t approaches -4 of. So the factor in particular that we must have is t plus 4, because we need to have a factor that goes to 0. So that must occur both in the top and the bottom, or the numerator and denominator. So now how do we factor the numerator if we have a t plus 4 as a factor? Well, difference of squares, that becomes t plus 4 and then t minus 4. Okay, so in our second equation though, you have t plus 4 and then what? Well, notice we have a -2 here times the t squared, so that's -2t, and then plus 4, and we need to multiply to -20, so that should be -5. And you can double check it. Use your FOIL method, check to make sure the denominator matches with the other, and when you just do that, go first times first, so you go there, outside times outside, inside times inside, and then last times last. That's all you have to do. But that's actually, you'll see that that works. And that usually tends to be the tricky part for a lot of calculus, is the algebra, right? A lot of people, it's not so much the rules that they'll learn in calculus, it's always the algebra that tends to trip people up. So the top part becomes t minus 4, the bottom part becomes -2t minus 5. And so now we're ready to plug in. Plug in -4 into the numerator, you get -8. Plug in -4 into the denominator, -2 times -4 makes 8, minus 5 is 3. And so that, in fact, is our final answer. Okay, so hopefully that makes sense on that part. Now we'll get to something a little bit more tricky. As I said, we try and generalize a lot of times. So off on the side though, I'm going to make a little note here. So you see a y cubed minus t cubed and a y squared minus t squared. Notice as y approaches t, you plug in t in for the y, you get t cubed minus t cubed, which is 0, and then you get t squared minus t squared, which is 0. So that does tell us something. It tells us that y minus t is a factor. And I know that might scare some people, so I'm going to kind of do an aside here real quick. What's actually happening? Hopefully you can recognize the bottom one, how to factor it, because it's basically essentially the same thing as what we just did up top, except we have the y squared in the first spot where the t squared is up in that first one, and then instead of 4 squared, we actually have t squared. But the top one is the one I'm more concerned about. So let's say we have y cubed minus 2 cubed. Right? Notice 2 is a factor of that, because, or y minus 2 is a factor of that, because you have 2 cubed minus 2 cubed gives you 0. So we can factor this thing as y minus 2, but then we need some other factor, and this is actually a perfect difference of cubes. And so you can check this out. So we need a y squared, but notice that gives us a -2y squared right here if we multiply these two. So we need to kind of cancel that out. And the easy way to do that is to add 2y, because now these two terms would make a positive 2y squared, so it cancels out and goes to 0. But when we did that, we get a minus 4y, but we can take care of that by adding 4, because that'll make 4y here. And notice that we finish with a minus 2 times 4, which is minus 8, which is what that happens to be. Okay. And so let's see if we can generalize this a little bit more, or do another example first maybe. So let's say we had y cubed minus 5 cubed. Notice 5 would be a value that would give us a 0, It's an equal sign, don't let your eyes fool you there. So we can rewrite this as y minus 5, and we need a y squared involved. So where do we go from here? Well, that's plus 5y, and notice we get minus 25y, so there's a problem there. And the way we take care of that, add 25, and you can multiply these out. Just remember to go to every term, and you will see that that cancels and makes things nice and pretty there for us. So in general, y cubed minus t cubed becomes y minus t times y squared plus ty plus t squared. And in the bottom, similar manner to what we did up top. If you struggle to see this, let me know. It's y minus t times y plus t. So all that was done here is just algebra. Okay? So we have no other tricks up our sleeve really. We just cancel those two pieces off because of the common factors. Limits allow us to make that cancellation. So we are left with y squared plus ty plus t squared. And now I know a lot of people might be tripped up on this part too. What's our variable? Well, our variables are y. It's always the first thing that's involved with the limit. So we're going to plug in t wherever we see a y. So what does that mean? Well, it means we get t squared plus another t squared when we go t times y plus another t squared. And hopefully you can recognize how many t squareds there are. And in the down below you have t plus t. Okay, so that makes 3t squared over 2t, and we're going to make one assumption, so t is not equal to 0, so this becomes, you can cancel off that square with that, so you can write this as 3/2 t if t does not equal 0. Okay, if t happens to be 0, then you just, it's really not that interesting, you just have it's still 0, but we'd have to do another little tidbit there. So, but hopefully that makes sense on that piece. If there's any questions, just once again let me know. Factoring trinomials, that might be one you want to have in your basket of tricks there too, just how to handle that. So after factoring, you can do tons of them with the factoring. And just remember, if you plug it in, you get a 0 on top, 0 down in the denominator. That tells you what the factor is, and then the rest becomes a little bit easier. So the trickier ones, though, are when we start to get into square root business. And so that's what we'll do here. So let's say we have the limit as x approaches 2 of square root of x plus 2 minus 2 all over x minus 2. How do we handle this? Well, the fractions make it difficult, I agree, but the square roots really make it difficult, because if it's back to polynomials, all we need to do is just pull out the factors. So the way we handle these are slightly different. We do this thing called conjugation. And the reason we do conjugation is this fact. So if you have like an a minus b, if we multiply it by a plus b, we know that we're going to get a squared minus b squared. And so notice that squaring there takes away the square roots. So this conjugation idea is what we do is we can't just go willy-nilly, but we can get rid of that square root by multiplying by its conjugate, is what we call this plus business. But we can't just multiply it wherever we please. We have to multiply by 1, and that's why you do it on both the numerator and denominator. And so you get by doing this with fractions. So now what happens is you get the limit as x approaches 2 of, well, so it becomes a square root of x plus 2, that quantity squared, right? Because that's our a essentially. So that becomes just x plus 2, and then minus, and I'll just write it out as 2 squared for right now, but the denominator is a little bit nastier. You get x minus 2, and then you have square root of x plus 2 plus 2. Okay. So the top factors to x minus 2 when you go x plus 2 minus 4. And then you have an x minus 2 and square root of x plus 2 plus 2. Okay, yeah. So I see a question. It says, can I explain how I got the square root on the bottom? So I'm assuming we're talking right here. Why do we do that? Well, notice this whole quantity, and I'll put a bubble around all of it. So I can't multiply by anything I wish. The only things I can multiply by to not change the equation is 1. And so if you take a look at that, that whole equation equals 1. So whatever I do to the numerator, I have to also do to the denominator. The same thing is going to apply to the next one down below. Whatever we do to the numerator, we're also going to need to do to the denominator. Okay? So wherever you choose to go ahead and try and use this conjugate rule, you have to do it to both the numerator and denominator. So as soon as we chose that for the numerator, that kind of forced our decision on the denominator. There really wasn't much choice after that. So hopefully that makes sense. Does that kind of clear it up, or do you need a little bit more explanation in terms of what's going on there? Okay, awesome. So now let's take a look. So we have x minus 2 in both spots. We can cancel that, and so that leaves us with a 1 up top. And I'm glad you're asking questions, so if any more pop up, just let me know. I'm glad to help. Okay, so what happens here? So now we can plug in. It's just a plug and chug time. So this goes square root of 2 plus 2, which is square root of 4 plus 2. So that's square root of 4 is 2. So that's 2 plus 2, which is 1 over 4. And that's our final answer. So now the next one. This looks all sorts of nasty. And I really dig this problem because when you think about it, how do we actually go about getting this conjugate? And does it work for us? Can we make progress? And that's what we'll see. I'm going to do this intentionally a different way than I usually would, just so you can kind of see how we can regroup and do things. So when you first look at this, we have square roots. And then when we plug in 1, notice we get 0 over 0. So that means we got to do something with it. 0 over 0 does not tell us much information. So we got to multiply by the conjugate. Let's work with the conjugate in the denominator first, because that seems like the more problematic spot. So when we do this, we go 1 plus square root of x, 1 plus square root of x. Right? So that makes the limit as x approaches 1 of, this becomes 1 minus, and then square root of x squared is just x. And it was 1 squared, but that just becomes 1, so there's not much to that. And then up in the numerator, we have a square root of x minus x squared times 1 plus square root of x. Okay? Now, you might be saying, okay, let's plug in 1. Notice you get 0 from this term over on the left-hand side, and then times 2, right? And then all over 0. But you still have 0 over 0 because it's multiplication. So how in the heck do we go about doing this? And this is where it can be tricky. We could have done it right out the gate, and that's why I said I'm taking a little bit longer, more roundabout way. Plugged in, we got 0 over 0. That means we have more work to do. We need to do something in order to figure out what this limit is. So the thing that we'll do now, notice we still have a square root in this part. Oh, okay, so the question was, why was it we conjugated by 1 plus square root of x? So when we have the 1 minus square root of x, you notice that minus sign, what it means to conjugate is basically use a different sign. That's it. So it didn't have to be 1 plus square root of x. I could have actually chosen the top one, and that's actually what I'm about to do right now, is work with the top one. Technically we needed to do both because there were square roots involved on both parts, and the one when plugging in, it became 0. Essentially what's going to happen at the end of the day, to give you more of a big picture as to what's going on, there's going to be a 1 minus x involved. Oh, instead of the numerator first? Okay, yeah, there was no rhyme or reason in terms of, so the question became, why was it 1 plus square root of x? Why didn't we work with the numerator first? You could have worked with the numerator. Denominator just causes more problems. Essentially what's going to happen here, though, we're just going to need to do both. That's all I'm getting at, is it didn't matter. Since we plugged in 1, we got 0 over 0. It turned out we needed to do both parts. And what this is actually telling us, it looks funky. If your algebra is really good, you could actually factor a 1 minus x essentially out of both of these parts. That's essentially what we're getting at. There's a slick way you can do that. But if your algebra is not really on top of things, I'd suggest just using the conjugation for now. So because that's a lot slicker of a move. So in terms of this numerator part now, so as Jeff kind of mentioned, hey, you know what? You just go square root of x plus x squared, and then but you need to do it on the denominator as well, square root of x plus x squared. But now, remember, multiplication, you don't need to multiply to each term. It's not like distribution. We can just multiply these two pieces in the numerator, so that's important. And so we go limit as x approaches 1. When you go square root of x times square root of x, notice that just gives you x. And then x squared times x squared, that gives you x to the 4th. Now I'm not done with that top. We're going to have a little bit more work. And then you have a 1 plus square root of x. And then we have a 1 minus x down below. Okay, this looks nasty, right? Plug it in, you still get 0 over 0. But we can factor that numerator a little bit more. Notice we have a polynomial now. And first things first, actually, let me make this a little bit simpler. We go x times 1 minus x cubed, and then 1 plus square root of x. Okay, I'll go back to that problem in just a second here. So there was a question on problem 1. I'll illustrate. Here, you're going to see the 1 will appear on the denominator, essentially. So you'll kind of see, and I'll go back to problem 1 in just a second, if that's okay. So what we have now, we have x, 1 minus x cubed, and 1 plus square root of x. Notice when you plug in 1 in for the x here in this first term, that's just 1. But you plug it into the second term, that's where you get the 0. So that means 1 minus x has to be a factor. And remember, we just talked about a difference of cubes. Just kind of setting that up for this problem. So we'll see how much you remember it. If you go difference of cubes, that means we have 1 minus x, 1 plus, it goes 1x, which I'll just write as x, and then x squared for that second term, and then 1 plus square root of x. And all this is over 1 minus x. Now, so to kind of illustrate what happened, for the problem 1, we're talking about, the question was, where did this 1 come from? And so I'm going to kind of come up here. Where did that 1 come from after we canceled out the x minus 2's? You're going to watch the same thing happen here. I'll show you. So this 1 minus x cancels, and so what the whole denominator becomes is 1, essentially. Right? Because you cancel things out. Think of it this way. If you have 5 divided by 5, what does that make? It makes 1, right? So that's all that's happening there. So we can actually rewrite this whole problem as the limit as x approaches 1 of x times 1 plus x squared times 1 plus square root of x. Okay. So now we have, this is 1 times 1 plus 1 plus 1 squared, which is 1, times 1 plus square root of 1 is 1. So that's 3 times 2, so that makes 6. And that's our final answer. Okay, so going back to this one problem, after the x minus 2's canceled, what does that make? Well, pretend this was, as I said, we'll use different numbers. Say this was 7, right? So you had 7, if I have 7 over 7, notice that can cross off and go with 1, right? And 1, we can put either in the numerator or the denominator. In this case, since there wasn't a number up there, it goes up in the numerator. That's all that we're doing there. So, oh, is it before I canceled x minus 2? I'm not sure. Is this in problem 1? Okay, so before I canceled x minus 2, so the step before, am I in the right spot? You're right here? Is that what you're looking at? So the question, so you had x plus 2 minus 2, the quantity squared. And then x minus 2. Oh, okay, how did that come about? Oh, that's no problem. Now it says x plus 2 minus 4. If I go 2 minus 4, that's negative 2. Does that make sense on that part? So hopefully that makes sense. If not, let me know. I'll be happy to clear it up. Okay, so just, yeah, sorry I did that a little bit fast. So x plus 2 minus 4 simplifies to x minus 2. Okay. Yeah, we don't plug into the x. That's a great, so the comment was, I thought you were plugging in for x first. We plug in x to check along the way. So, but the big thing that you want to do is you don't plug in until you have it down where it isn't 0 over 0. So you keep on checking, but as long as it's 0 over 0, we got more work to do. And that's all that we're doing. So we're just simplifying. It's telling us there's a certain factor. If you notice, we plugged in 1 into this last case. We ended up with factors of 1 minus x canceling. We know we kind of know what our factors are going to be right away. It's a matter of breaking it down that way. Okay, so yeah, I see there's a question about the algebra number 2. Yeah, sure, so most definitely, ask away. What line are we looking at where the question on the algebra is? My guess might be that it's right here. Oh, line 1, okay. So, awesome. So which part of the algebra are we looking at where the double arrows are? Oh, okay. So yeah, how do we distribute that? Okay, so I see what you're getting at. So you're wondering probably why do we just go those two terms to multiply? And I'll give you more of an example with numbers as to why this works. So say I had 2 times 5 times 2. Okay, if I multiply this, notice I get 20, and most of you might say, oh, that's easy. But what a lot of people think is that you have to multiply, so I'll put a big question mark here. Then you multiply each of these. But notice if I go 2 times 2, I get 4, and if I go 5 times 2, that's 10. That would be 40, right? And that does not equal our answer up above. So what you do is you can pick which term you want to take it to. And so in this case, the only reason I said that these two should go together is because they're conjugates, and it's going to make it simpler. Right? I could have chosen the other one, it just wouldn't have made any progress. So that's kind of the practice of this, is those two are conjugates of one another, because notice how you have a minus in one case and the plus in the other. So we knew right away that we could use this property, this a minus b quantity times a plus b quantity, to equal a squared minus b squared. So yeah, you don't distribute to both. It's not addition, right? It's multiplication. So yeah, when we're dealing with multiplication, you can pick and choose which one you want to multiply that term by, right? So if it's addition, it becomes a different case. So keep that in mind when we're doing that you're going to see that pop up quite a bit. So common thing that happens too. So hopefully, does that clear it up then on that problem? Yeah, and that's the big thing. I would always recommend, if you're really not sure right away, always go to numbers, right? Notice I just brought out some numbers there to try and illustrate what happens. If I'm not sure on a property, go back to the numbers, because that's where all this algebra is lying, right? It's just based off of numbers. And you have calculators and stuff to help you. Obviously not on an exam, but it can help you along the way. So now let's move on to infinite limits. I just want to touch on a couple of these, and maybe do a graph, and then hopefully we'll call it good. So I'm actually going to start with number 2, just because to try and illustrate what's happening here, the big picture, and then go back to number 1, kind of show you how we can use these ideas in both places when we have roots involved. So anytime you see an infinite limit, what that's actually telling you is telling you the horizontal asymptote of the graph, meaning the y value we approach as x approaches infinity. Sometimes they exist, sometimes they don't. So keep that in mind. Now, with this one, the things we always look for are the degrees of the polynomial. So I'm looking at the degrees right here. And what we do, there's a couple ways to do this. I don't know if you want to see both or how you want to do this. The way, I won't write equals just yet. One way is you can factor it out. The other way is you can multiply, so it doesn't really matter. I'll start with the multiplication, then I'll show you the factoring method. So notice the degree of the polynomial is 2, so that's what we're going to multiply by. and I always just go with what's in the denominator. It makes it easier that way. So if I go 1 over x squared, remember I have to do that up in the numerator as well, and I will need to distribute in this time, because notice there's 3 different terms with minus and plus signs. There's not multiplication times each piece. So I'll need to multiply this 1 over x squared times each piece. Now you might be asking, why are we doing this? So there is something lying on the sidelines here that I'm actually about to make use of. So when we actually do multiply this one out, we get 1 minus 11 over x minus 5 over x squared. And then we have 8 over x squared. And then minus 9x squared over x squared just makes minus 9. Okay. So the thing we're using on the sidelines here, if you have, let m be greater than 0, and c a constant, the limit as x approaches infinity, doesn't matter where c is, of c over x to the n. Now n, it has to be a positive in that denominator. That will always equal 0. That's what we're going to make use of. It seems tricky, but it's really a useful tool. So, and I'll show you why it's useful. When we take a look at this limit, where's this thing going? Well, it's 11 over x. That's a constant over x to some positive power. That's 0. What about this 5 over x squared? That's a constant over some x to some positive power. That means that's 0 by this result over on the sidelines here. 8 over x squared. What do you know? That thing's also 0. And so this whole thing just equals, we have 1 minus 0, which is just 1, over 0 minus 9, which is just negative 9. So this whole thing equals negative 1/9. And that's it. That's all there is to it. It's not the only way, though, as I mentioned. Some people like to factor. So if you like factoring, you could have factored out an x squared. X squared times what gives you x squared? Well, that'd be 1. X squared times what gives you 11x? Well, that'd be 11 over x. X squared times what gives you negative 5? Well, that'd be negative 5 over x squared. Okay. So yeah, and so I see the comment, powerful rule. Yeah, most definitely, you need to know that one. That's one that's going to take you a lot of places. And even if you have to go into Calc 2, you're going to basically be comparing a lot of ideas of how fast things are going to either 0 or infinity. And I'll kind of give you an idea in a second. So you said c has to be positive for that rule to work. Actually, I kind of misspoke if I did say that. C can be any constant. N has to be positive. And the reason why, if n is a negative and it's in the denominator, that moves n back up to the numerator. It's just kind of a little trick. So in terms of the replay, can we replay these after we're over? Yeah, some of the main rules, I just say, yeah, you can take a look at these. And yeah, I'm actually going to post this YouTube live session on our class page, so you'll be able to see this again too. But yeah, make sure it is a powerful rule. Make use of it. And I'll kind of show you a neat little trick too, if you're interested as well, where this stuff comes into play. So notice factor in the denominator. If you factor out that x squared, you get 8 over x squared minus 9. So notice this thing becomes, the x squareds cancel, get the limit as x approaches infinity, and what do you know, we get the same sort of setup there. And notice that means same rule. We'll get the same result of negative 1/9. It's exactly the same thing as what we had right here up above. Those two are the same thing. So, moving forward on this, let's go back to number 1 now. And the reason number 1's tricky is because we have that square root. So in order for us to do this one, we can look, and the degree here is to, I could circle the degree, but with that square root, it might be a little bit trickier. Remember, square root is x to the 1, or I shouldn't say x. Square root means to the 1/2 power. Doesn't mean you can break it up across the pluses and minuses, though. That's a big mistake that people make. So we have a little bit of work that we would need to do. But what we'll do is we'll multiply by 1 over x squared and 1 over x squared. However, notice we have a square root. In order for us to do that, what we need to do is we need to square this and take a square root there. Okay. I should give you a warning. This can be tricky when we're doing x approaches negative infinity. Since this is an x squared scenario, not a big ordeal. We don't have to worry about absolute values and things like that, but sometimes when we're squaring things, you can turn negative values into positive, so we have to be careful in those cases. So now, what happens? Well, this gives us the limit as x approaches infinity. Remember, distribute to the denominator. So I'll start with the denominator, actually. That'll probably be a little bit easier. You have 3 over x squared minus just 7. Now the numerator, notice this thing is just the square root of, you get 1 squared, which is 1, and then x squared is x to the 4th. So now we can take 1 over x to the 4th. Since we both have square roots in both parts, we can multiply that on through. So notice that gives us x to the 4th over x to the 4th, which is just 1. 3x cubed over x to the 4th, that's just 3 over x. And then 7 over x to the 4th. Okay, so let me know if that causes any problems or anything like that. Hopefully not. Okay, so now let's use our rule again, right? So limit as x goes to infinity, this thing goes to 0. What about this 3 over x? Well, that's a constant over x to some power. That's positive, and then same thing with this one. So notice what we're left with is just square root of 1 over negative 7. So that's going to be negative 1/7. And that's our final answer. Okay. Another way, once again, you could have done this factor out. And what I'd say is always factor out the degree of the polynomial. So this could become 3 over x squared minus 7 all times x squared. And then in the square root, you get x to the 4th. If we factor that out, we get 1 plus 3 over x minus 7 over x to the 4th. So notice, when you actually do this one, you get square root of x to the 4th, which is just x squared essentially, and times another square root of 1 plus 3 over x minus 7 over x to the 4th. Oops, don't need that extra parentheses there. And then we have x squared, and then 3 over x squared minus 7. Okay. And notice what will happen. This becomes x squared, and that'll cancel with that, and you're left to finish off the problem. And so, great question. What if the square root is on the bottom? Notice if I just, I could just reverse the roles, right? If you struggle with the square roots, the way I always think of this, and if you notice, now these two were very particular. I wanted them to be numbers that are non-zero and things like that. If the degrees are the same, so notice those 2 degrees are the same, all you needed to look at was, oops, the negative 9, and then there's a 1 sitting right here, so negative 1/9, that was our answer. You'll learn if the degrees are the same, no matter what it is, you just look at the constant term multiplied by the degree. That actually is what your limit will go to. In this case, it looks tricky, right? But what I'd recommend, kind of noticing, if I take the square root of x to the 4th, notice that's the same thing as x squared, right? So essentially I'm going to have x squared over x squared. As long as you're looking at the degrees and you know how to make that manipulation, you're going to be in good shape. So that's all I was doing in that problem, right? Hopefully that makes sense on the square root. If it's in the denominator, you can do the same song and dance. I just use the one, you could use the degree of the one that doesn't have a root involved. Or if both of them have roots involved, just try and see, take the type of root of the degree and see what happens. So if there's any more questions, just let me know on that. And you'll have some practice. I left it open. I didn't want to do tons of problems because I want you to practice them. That's the main thing. And you can always send me your work and let me know where the struggles are and stuff. Okay. So last one here, infinite limits with graphing. All right, how do we handle these things? Let me bring in a new color here. Okay. Evaluate the following limits. The limit as x approaches 0. So notice, in this case, as x approaches 0 from the left, we're going down, 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 down forever and ever. So it seems like we're going, y value is approaching further and further down towards negative infinity. Same thing is happening from the right hand side. You're going down, 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 down towards negative infinity. So the limit as x approaches 0 of f of x is negative infinity. But what this tells us actually is something else. It tells us vertical asymptote. Anytime you have a limit, whether it's from the right, from the left, as long as it's approaching some positive or negative infinity, we have a vertical asymptote at x equals 0. As a matter of fact, you actually have some more vertical asymptotes. So if you notice, we approach 4 from the left. Don't let your eyes fool you there. That's a straight dotted line. I promise I haven't been drinking. So if you take a look at that, notice from the left-hand side, we're talking the graph is right here. We're going up, 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 up. And so we're going up towards positive infinity. Oh, that got kind of funky. And also that tells us some information. That tells us we have a vertical asymptote at x equals 4. And so notice I can start listing out vertical asymptotes. This is based upon where it's going to positive infinity or negative infinity. Now, the limit as x approaches negative 2. So notice from the left, what do we have? Well, it's approaching 1 at that point. And then from the right, it's approaching negative infinity. So while we do have an asymptote, because one of those limits is approaching negative infinity, this thing is it does not exist because the left and right hand limits are not equal. Okay, so now on to the limits as x approaches positive infinity and x approaches negative infinity. So for positive infinity, what I'll do is I'll start to draw a line. And graphically, this isn't the greatest thing, but what this tells you, notice how this is seeming to get closer and closer to this y value, but never quite touching. And granted, it did cross earlier, but as we go further and further out. So notice that y value is negative 3, and what that tells us is the limit as x approaches positive infinity equals negative 3. That tells us more information. This relates to the previous problems. It's the idea of a horizontal asymptote. Meaning as we get really large with our positive numbers, so we have y equals negative 3 as x approaches infinity. And then notice on the other side of things, whoops. Once again, do not let your eyes fool you. That is a perfectly straight line. So our y value, as we approach negative infinity, we're getting closer and closer to positive 2. So this thing equals 2. So y equals 2 as x approaches negative infinity. And so you have horizontal asymptotes, you have vertical asymptotes, all sorts of stuff happening right there. Okay? So I don't see any more questions. Hopefully this can help you with the homework, and hopefully it opens your eyes to a few more possibilities when it comes to the problems. So if you do have any more questions, please post them in the discussions and let me know. You can also email me or stop by during my office hours. Okay? Hope you all have a great rest of the week. Oh, okay, so I had a question. Before I cut out, can you explain the vertical and horizontal problems without a graph? Like when a problem describes that the limit has, and so I don't see what the rest of that question is. Yeah, I can definitely explain what happens here. So with this problem, right before, we had a limit as x approaches positive infinity of this whole equation equaling negative 1/9. What does that mean? It means we had a horizontal asymptote at y equals negative 1/9. Okay, so to explain a little further, I might not know jack squat about this graph, and I'll be honest with you, I have no idea. I don't have anything by me. We'll learn later. We can figure it out in great detail. But one thing I do know right out the gate, and what you'll learn in time, is you can do these things kind of in your head if you practice them enough. It just takes time. You got to take the time to practice, and you'll start to see some of the trends and all that stuff. But to kind of relate what's happening here, here's all I do know. I don't know much, but I do know this about the graph. So say this whole crazy business of function x squared minus 11x all over 8 minus 9x squared. I have some graph, and I don't know much, but let's say negative 1 is right here. So negative 1/9, it's really close, hugging that line, right? So I don't know which side it's going to approach. So it could be from this side, or it could be from this side. But I know one thing's for certain. I'm going to be approaching this line as I go to infinity. This is going to be y equals negative 1/9. And so this graph of f of x, where f of x equals x squared minus 11x minus 5 all over 8 minus 9x squared. Don't know much about it, but I do know what's going to happen there. Now, in time, we're going to learn more about how to deal with this graph and actually get all the information to graph the whole thing. That's what we're gunning for. So, but right now, this is just one small sliver of what's happening. We'll be able to tell you which side of this line this will come on, all sorts of stuff. When it's increasing, when it's decreasing, when it's concave up, meaning looking like kind of like a parabola, or when it's concave down, looking like a frown of a parabola, I guess I should say, and all sorts of different information. So, but hopefully that makes sense in terms of what's happening just from getting an infinite limit. So we have a graph connection, and that's what we're really looking for. So, any more questions then on this? Oh yeah, so it said the homework set asked for the equations of asymptotes in increasing order. So this is a slightly different graph, by the way. I always change it up just slightly, make you do a little bit more work. So if you look at this problem, from the vertical asymptotes, notice it's always talking about x equals. So if we went in increasing order, the smallest is negative 2. So x equals negative 2. Then the second is x equals 0. And then the third is x equals 4. And so in the second one, we would do same thing, y equals negative 3, and then increasing to y equals 2. Okay, so it seems like you got it. Any more questions in terms of what's going on? Okay, wish you all the best of luck with the rest of the homework, and hopefully that makes more sense on the earlier homeworks and whatnot. So have a good night.